Now, at this time, I'd like to hand things over to Director of Marketing and Business Development at Evonik Jayhawk Fine Chemicals Corporation, Boris Shafran. Boris, go right ahead.
Thank you. This is Boris Shafran, and we welcome you to the next in a series of joint webinars put together by Evonik and Dixie Chemical, where we explore the benefits of combining monoanhydride and dianhydride technology as thermal curatives for epoxy resins in a variety of different applications. We'd like to spend the next 30 minutes or so with you today, focusing on the first part of our findings, where we are starting to see some very interesting results regarding the improvement of performance properties of epoxy syntactic foams, which are now being placed into more demanding service environments, deep water applications, more aggressive chemical environments, and we have found that the focus on the curative component can actually drive very significant improvements in overall performance properties. So thanks again for joining us, and please stay with us as we present to you the rest of our findings. Okay then, so the landscape that we're really talking about is the deep water exploration of oil and gas reserves. And whether you follow that in the newspaper or that's part of your daily business, I think we're all starting to become aware of the fact that in order to tap into these underwater reserves, much greater distances are now being required. So, a reach out distance of 30 miles. I mean, think about that. 30 miles of piping and the demands that are being placed on that piping to adequately transport crude oil, natural gas, from the ocean depths to the surface. That means that higher subsea oil temperatures are being encountered. Greater hydrostatic pressure against the pipe walls now commonplace at these deeper ocean depths. Overall enhanced corrosivity. The need for insulation becomes important. So there are different configurations to consider. The first would be a pipe-in-pipe, which is fairly straightforward setup. The second would be flexible insulated pipe, which consists of various types of jacketed layers, and the advancements in thermoplastic technology are really driving that type of a configuration. And the third is syntactic foam, and syntactic foam being a rigid material protecting a rigid pipe or different types of equipment as a cladding, and with one side against the pipe interface and the other against the ocean water. That syntactic foam and the chemistry of that foam, the formulations for those foams are really something that you can optimize and improve their properties, and that's what we've tapped into with our curative study. Okay, so now that we've set the stage, I'd like to quickly just review the research goals of our study. And part one is what we are presenting to you today. That's where we have started our investigation of how different monoanhydride and dianhydride blends can work effectively as thermal curatives for epoxy-based syntactic foams and really improve the performance properties, specifically addressing some of the things that we just covered. Part two would go into greater depth, and that is something where we would be looking at modeling, where we would take the optimized blends and start to build models so that we could predict in-service performance, different formulations, different depths, and make the job of the formulator that much easier. Part three would be where we would actually take some of these optimized formulations and fabricate parts, put them into service, and monitor them so that they're doing exactly what is being predicted by the models. So this is a longer term study, and part one is now coming together very nicely, and that's what we're very eager to share with you today. So we spent a lot of time talking about syntactic foam, so let's take a moment here to better define it. And the term foam is a bit of a misnomer, but let me explain. What we're talking about here is really a closed cell foam material, and the porosity in the foam is provided by hollow glass or ceramic microspheres in some type of a binder. Can be organic or inorganic binder. So this is a rigid foam material. If microspheres are used, it's a syntactic foam. It can also be blended with larger macrospheres to create what's called a composite syntactic foam. So the syntactic foam is really the reference to bring together different materials. Think of syntax and how a sentence, sentence elements are combined. This is the same kind of logic. So this type of formulation provides a number of different things. It's obviously low in density, so it's lightweight, provides buoyancy. The round microsphere walls are very good with regards to compressive strength, so high hydrostatic pressures can be withstood. This insulating quality, due to the low thermal conductivity, allows the internal pipe temperatures to be maintained, so you've got reasonably good fluid flow, and preventing things like paraffin formation. So the depths, 10,000, 15,000 feet, are really the target here. So thermal insulation of piping, pieces of equipment, manifolds, and other things like buoyancy for drill risers, even deep sea vehicles, which is used quite prevalently. So there are many areas in which syntactic foams are used, some quite unusual ones, but this is where we see the benefits of paying greater attention to curative technology. The critical factors for the proper performance of the syntactic foams come down to a number of different requirements, and you see some recurring themes here. Before I get into that, just want to direct you to the nice micrograph here on the right, which gives you a really good view of the glass microsphere and the dispersed organic phase, the matrix, and it can be quite fragile, that interface, and the simple formulation has a lot to do with that, as you see here. So when we talk about weight and actually weight reduction, that means we have to look at density issues and buoyancy if that's required. It's a function of the sphere wall thickness, the loading level. Loading level also comes into play regarding the ability of the foam to withstand hydrostatic pressure, basically the compressive strength of the foam. The shape of those spheres, the nice round shape, obviously is going to give you very good resistance to compressive strength, compressive forces, but the wall thickness is equally important. So sphere wall thickness and loading level also come into play regarding insulation and the need to have the lowest possible thermal conductivity to truly insulate the pipe and its contents. The ability to withstand heat is a function both of the microspheres as well as now the binder. In this case, the matrix, we're talking about epoxy as the dispersed phase. Epoxy glass transition temperature can be absolutely improved via optimal selection of thermal curatives. The opposite of that would be in the case of overall integrity of the foam to resist cracking. Here you'd actually want the binder to be a little bit more flexible, so and perhaps adhere to the spheres if that's necessary. In some cases you do not want sphere adhesion, but so you have to strike a balance between those two. Water absorption is going to lead to ingress and slow degradation of the foam itself and just a deterioration of the foam. Binder selection comes into play there. So you see all the raw materials that comprise the foam have a role to play. And if those can be put together in an optimal fashion, you can certainly drive performance, extend the service life, and improve the overall performance of the material in service. And that's what we're driving at. So of the different syntactic foam formulations that are available today, The workhorse and the one with a fairly long established track record have been those based on epoxy resin chemistry. Very standard DGBA resin is utilized, and that type of resin can be cured under ambient or thermal curing conditions. Elevated temperature curing is really the way to go in order to drive the properties that we have been mentioning so far. And the monoanhydrides listed here have been the traditional go-to curatives. The more flexible DDSA on the left and the more rigid MTHPA on the right are used in different combinations with this standard epoxy resin and can produce very suitable epoxy syntactic foams and work well in service. There are other types of polymer technologies that are coming on board now to fit into more niche applications, producing very intriguing properties, and those are listed here as well. But what we decided to focus on is how to improve that curative package. And we know that the inclusion of dianhydrides that are known for good elevated temperature performance, if they're introduced here as well, you can put together some very interesting properties and make some very nice jumps in some of those things that we were talking about before in order to really drive performance. And that's what we're going to show you next. So anhydrides as a class of materials include both monoanhydrides and dianhydrides. And the easiest distinction for you is that monoanhydrides are traditionally liquids. So right away that's interesting because they're easier to mix and easier to process the syntactic foam formulation. One such example would also be something like natick methyl anhydride. Solid dianhydrides, BTDA being a prime example, are really known for sustainable properties under higher temperature conditions. So they seem very well suited for this type of formulation. The hindrance is that these are solids. So now you're trying to disperse a powdered material into this mix, and you can understand some of the hindrances and the aggravation involved in doing that. So if you can put blends together, this is where we see a benefit. And if you look at this quick little graph showing different levels of glass transition performance, you see that when you start looking at liquids and maybe incorporating with the dianhydride, you can really make a marked increase in TG and drive some of those things that we've been speaking about: heat resistance, and overall performance of the syntactic foam in service. It's our opinion that blended curatives with dianhydrides become the gateway to really addressing some of these formulation challenges that the market is now presenting. Rigs being placed farther offshore, deep water explorations requiring much longer lengths of pipe, as we had mentioned, higher hydrostatic pressures, higher crude oil temperatures. So there's an opportunity here, and this is why we want to explore the benefits of new types of blends to really serve as a better class of thermal curative. Here we show the give and take between putting a blend together and what impact it has on processing, on properties, and some of the downstream performance. You would think that you could simply swap one anhydride for the other and you would be fine and you could carry on with your existing formulation. And that's simply not the case, as demonstrated here. We show a blend of BTDA and MTHPA, so you've got a solid, finely divided particle, and you've got a very low viscosity liquid being put together in different ratios. And in a syntactic foam formulation, an uncured formulation, clearly you see a viscosity improvement as you add more monoanhydride. I think that's fairly straightforward. But it shows you some of the pitfalls, especially if you would try to make a formulation purely with a solid dianhydride. What would be involved there? From a cured material standpoint, now you start to see some of the trade-offs or the improvements actually. From a glass transition temperature, now you see with the dianhydride going down to the monoanhydride, a very significant drop in numbers, as much as 10 to 15 degrees, which can clearly influence the performance of the syntactic foam. From a flexural strength standpoint, you see some not too much difference, so there's a little bit of a trade-off there as well. So you've got to decide what's important to you and which formulation is best suited for a particular type of service. And in doing so, then you can go back and fine-tune your mix of dianhydride and monoanhydride. The other thing to consider is that when you do put these blends together, there is a critical amount of dianhydride which is required in order to affect the change in properties that you're looking for. So if you decide to add only a little bit because you want a very easy to handle processable mix, you may not even be getting any of the results that, the benefits that you're looking for. So there are many trade-offs, and it makes the blend composition that much more complex. Here's an example of some of the data which is starting to come in from the study. You've got hydrostatic crush strength as a function of uniaxial compressor strength, something that can be easily measured in the laboratory, against something that would be more indicative of material in service. And there's a clear relationship between the two. One mix which we formulated gave us a compressor strength of 104 megapascal, which correlates to about 120 megapascal of hydrostatic crush strength. So those are very impressive numbers. And if you further correlate those with in-service depth, which can be done, that comes out to about 34,000 feet. Which is well beyond the 15,000 feet that we've been using as a house figure so far in the discussion. So the potential for these blended systems to far surpass the current state of the art is clearly demonstrated here and illustrated, especially by the glass transition temperature, which was obtained here, which is 232 C. Clearly a good 20 to 30 degrees higher than anything that is conventionally in use. So the opportunities here to improve and to optimize these formulations based upon greater scrutiny and more careful attention to the curing package is clearly something that requires greater attention. All of this then begs the next question, which is where do we go from here? And there is a lot that can be done to further optimize these systems. All of the raw materials can be studied in terms of the different variations that exist out there. The standards are good. Now that we're starting to investigate curative systems, we see the possibilities for improvement. So all of the raw materials obviously can be investigated, and that's something that we will start to look at in the months ahead. The phase 2 and the phase 3 will come later on once we have a much stronger grip on the variables and how they are driving the different levels of performance for us. So far, samples that we have made, here's an example of a loaf of syntactic foam which was mass cast. These samples are being produced for us, and they are of very good quality, extremely low, insignificant porosity. Very good examples which we can use to generate a much wider data set, which will further support the claims that we're making. Time then for conclusions. We've demonstrated quite clearly that syntactic foams are a key technology for deep sea exploration, and the benefit of their properties can be achieved by a much more careful examination of formulations, particularly in the area of epoxy systems, where the thermal curatives, we know they have played a role, but now we can see how they can play even a more greater and significant role going forward. Blended products allow us to incorporate and examine dianhydrides as a means to really tailor properties of these syntactic foams for oil and gas applications. The modeling step will come down the road, and that will be very critical to formulators to save them the time and trouble of their own trial and error experiments, and rather plug in and select for their given application what the optimal formulation would be. That's a direction that we clearly want to move in, and some first steps are being made in that direction. It's my great pleasure to acknowledge and give special thanks to two contributors that have really helped us put this program together and produce these very interesting results which have intrigued all of us. Dr. Gary Gladitz, who is serving as a consultant, has played a vital role, as well as Dr. Brian Pillay and his staff at the University of Alabama, Birmingham, who has been very active in building and conducting the testing program on our behalf. Thank you, gentlemen. We appreciate you staying with us through the webinar, and we thank you kindly for your attention. The collaboration between Evonik and Dixie in the area of epoxy thermal curatives has proceeded on a very strong note, and we hope that this information helps you, and we look forward to answering your questions and hearing your comments, and any follow-up service that we can provide, we will be glad to do so. Thank you very much, and our very best to you.
Okay, I have a first question here. What types of accelerators can be used for curing epoxy? Vinay, can you answer that?
Sure, Jane. Take a shot at it, and then Jeff, feel free to comment if you want to add something to my answer. So just like any monoanhydride epoxy reaction, you would use the same kinds of catalysts and accelerators as with the BTDA systems. The common examples are tertiary amines like either BDMA or DNP30 or imidazoles. And then you can also use latent accelerators instead of actives based on your process. Current work that we're doing is actually using liquid accelerators for ease of incorporation in the system, and we will be also looking at additional accelerators even if they are not liquid.
Yeah, Vinay, I would agree. In general, you're looking at materials that can react with the anhydride group, open it up to start forming hydroxy groups, which then promote the polymerization to occur. So amines, imidazoles, things like that that have been used historically as epoxy curatives or accelerators, can be used with both dianhydride and monoanhydride systems.
Yeah, I agree. This is Boris, and I'd like to add for the audience also that this type of chemistry involving epoxy and anhydride cure is quite versatile in that you can really design different types of processing windows. You know, these can be very rapidly cured. These can go out to minutes or hours if necessary. But for mass casting of syntactic foams, if you're looking at deeper depths or thicker materials where exotherm is an issue, this type of curing chemistry really works very well to that and minimizes exotherm and improves dimensional stability of the castings.
Okay, thank you all. We have a couple of general questions about porosity. If you could address that, probably all of you.
Sure, this is Boris. I'll start. I mean, we identified some of the issues relative to porosity. The first thing, obviously, is the desired porosity that you do want by incorporation of the micro or the macrospheres in order to boost the insulating properties of the syntactic foam. What I gather from a lot of the questions here is that there are concerns regarding processing, right. Mixing techniques and so on, where maybe you're introducing porosity or attempting to remove air and such from the system, those would be a slightly different consideration. Jeff, would you like to comment on that as well?
Well, yeah, I think that you're using the microspheres, the additive, to give you the density, give you the compressibility you want. If your formulation, your agitation is bringing a lot of air into the system, you need to really thoroughly degas ahead of curing, so that you really are in full control of the material that you're working with. If you introduce various amounts of air or other gases in the system ahead of cure, then you're not going to be seeing the benefits you think you are based on the formulation and the type of microsphere that's used.
The nice thing is that these type of formulations are pretty clean. They're solvent-free, so you're not introducing any concerns regarding porosity that way in terms of solvent liberation. And the samples that we have seen and that our testing partner continues to prepare, rather straightforward methods, nothing too sophisticated to mass cast these,
right.
And the quality is surprisingly very good. So it seems to be pretty much under control with rather simple processing procedures.
Okay. Anyone else? We're all set there?
Okay. I think we're set, yeah.
Okay. There's a question, what is the best sizing for coating the microspheres?
Well, thanks. This is Boris, and there's a lot, there's a lot of differences of thought with regards to that. In many cases, you don't, a normal system where you put in some type of a filler and you want to match the filler surface with the binder, and you come up with particular sizings that from a chemistry standpoint you have some compatibility. Here it's very dependent upon what the intended surface of the end foam is going to be. In many instances, you want the microspheres unbonded, right, so that they can move, so that there's some further insulating effects from that. If you introduce a sizing of some kind, and now you've got the whole thing bound into a monolithic system, you're also introducing quite a bit of, at least you're increasing the
strain and.
Absolutely, and there's going to be additional rigidity there as well. So
it may actually result in poor performance of the material over that that's unsized.
It's very application dependent. You could think, well, I want sizing because I want proper bonding. I don't want water ingress. I want the highest possible compressive strength. But then the flip side of that is I want them unbonded so that I gain best possible insulating characteristics. So it's a balance. And I don't have a one-size-fits-all answer for that, but what we've seen is that it's very application dependent, and I'll leave it there.
Okay, thank you, Boris. Next question is, why haven't thermal curative blends been investigated before?
Well, they have been. It's dianhydrides. The original development of dianhydride was based as a thermal curative for epoxy resins going back some 50 or 60 years. What we have found over the years is that some of the technology, some of the performance characteristics of the dianhydrides have been lost, and this type of webinar and others that we have had in the past are just simply re-informing people about the capabilities of what these types of hardeners can do and be used in the system.
Absolutely. Yeah, this is Boris. I'll just add some additional comments there. The reason and the start of the program here to investigate syntactic foams is that we really have not seen where dianhydrides have been introduced into the cure package. So in this particular application, even from the initial work that we have done and we have presented this morning, you're starting to see some very intriguing results. So there's definitely a place for dianhydrides here. Have they been investigated? We have not found anything. So that's why with this study we want to begin that and to start to educate everyone as to the possibilities and the opportunities that exist. Yeah,
but I think we want to be clear that they may not have been investigated with respect to syntactics, but have been used for investigated heavily for other epoxy systems.
Yes, good point. Good point. hope that addresses the question.
Okay. Thank you. And is epoxy the best choice for syntactic foams?
I'll start on that one. Is it the best choice? It is certainly the most popular choice. It has been used for some decades already. There's a significant use history. The thing about them, though, is that the focus has been on the rather simple side of epoxy chemistry using DGBA resins, which seems to be perfectly suited for this application. So there's a good use history. There's a reasonable track record. Epoxies are probably the most versatile in curing them and delivering certain types of performance properties. So that's probably where you're going to see an edge over some of the other up-and-comers, that we had mentioned before, which are really relegated to much tighter applications. So epoxies have more widespread use. And, our main message here today is that they can be tailored and optimized even further by just taking a fresh, sensible look at the curing package.
Okay. Thank you. And how about what is the importance of micro or macrospheres?
Sure, I'll take a crack at that. The various types of microspheres, micro balloons that are used, they can vary. If we just stick with micro balloons for a second, we can talk about either glass or ceramic chemistry for those. Typical sizing is on the order of about, less than 100 micron. Glass would certainly be the most prevalent type that is used. There's a function of wall thickness that we talked about before in terms of overall strength and insulating qualities and so on. So it's the most prevalent. Microballoon purity is also of importance as well. So in some cases, you see microballoons being mixed with macroballoons for composite syntactic foams. And in these instances, the macroballoons are, for the most part, low-density expanded polystyrene in chemistry. And what you see there is these are much larger particles on the order of, let's say, 3 millimeters or so you can gain an appreciation of what we're talking about. And you'll see instances where they are blended together to affect certain degrees of insulation, thermal conductivity, things of that nature.
Okay, thank you. What impact does the use of the foams have on flow line installation procedures?
Sorry, we're just kind of reacting to that question. I'm not sure that we can fully address that here. I mean, we are talking about precast, mass cast materials as opposed to cast in place. I don't know if that's what the questioner is getting at.
We can follow up.
I think the best thing to do is to follow up with the particular questioner and address him offline.
Okay, that's fine. And are samples available, and if so, who is the contact?
Samples are generally available either from ourselves, Evonik, regarding dianhydrides, from Dixie Chemical regarding the monoanhydrides. What we like to focus on here, though, is that blended systems, which will offer much more versatility to the end user, will be sampled starting in the early part of next year, and those will be available through Dixie Chemical. So you are welcome to follow up with them, and Vinay, who's with us here today, would be happy to field your inquiries.
Yes, that is true. I'm not sure if my contact information is available to the attendees, but I'm sure we can do that in a follow-up email to the attendees.
Through the Dixie website or through the Evonik Jayhawk site. Yeah.
All right, thank you. Is syntactic foam compressible like a conventional foam?
I mean, the primary difference here is that we're talking with, we're discussing a closed cell foam with a rigid structure. I guess there's no better word to describe it than foam, because technically it is a foam, but the foam that I think of is a sponge that I use when I'm washing the dishes.
Yeah.
So it is a foam by virtue of the fact that it has porosity which has been cast into the composite. But these are quite rigid systems and purposely formulated to act as a cladding, for these different applications that we're discussing. So it's an unusual term, but it's the term that industry recognizes for this type of composite material.
Yeah, they're more resistant to compression as opposed to a traditional foam, I think is maybe the better way to look at it.
Okay, very good. And here's a general question. What role do dianhydrides and monoanhydrides play in tailoring performance?
I can take that, Jane. This is Vinay from Dixie Chemical. So as Boris pointed out in the webinar, the dianhydrides like BTDA boost the TG because of the cross-link density that they impart to the epoxy resin that is cured with them. And they also help achieve very high compressive strength. While they have these great extreme properties they're able to offer, it helps to include a monoanhydride in a realistic formulation, which is, I believe, also was pointed out by Boris, that you want to make the system easy to use. So a liquid monoanhydride present with the BTDA helps in incorporation into your recipe, creates a better intimate mix of the resin and the curing agent itself, which of course helps with the proper cure for the system and gets much better overall properties. In addition to that, the presence of some monoanhydride also helps balance the brittleness of the system and the TG, balance the necessary flexibility that the system still needs along with the high TG. Because if you actually have just BTDA as your sole curative, you could get a system that is perhaps too tightly cross-linked, and it may not be the best choice based on the exact service for the cured system. So having a monoanhydride helps balance out the cross-linking or the degree of cross-linking and keeps the overall system a much higher performing system. Boris, would you like to add something?
Well, I'll step in a little bit. As you've given a good summary there. The way I look at it, Vinay, is that the monoanhydrides have their place, and they've got their advantages and their disadvantages, just like dianhydrides do also. And what you find is you mix them together. I almost look like it as if it's a synergistic effect between the two compounds, being able to give you final cured properties that are, in my mind, better than either if you just use the single curative as your choice.
Okay. Any further comments?
No, keep going, Jane. We're doing good.
Okay. Well, we have come to the end of the question session here. So if there's no other comments, I would like to thank everyone for spending the time with us today. You're welcome to visit our two websites. That would be jayhawk.evonik.com and dixiechemical.com. And thanks again for taking the time to learn more about improving the performance of epoxy syntactic foams. Take care.